Bernoulli's equation. In Bernoulli equation, I think you have already studied. The equation will be like this: v square by 2g plus p by rho g plus z equals constant. This is the simplest form of Bernoulli's equation. This is called energy equation also. This, you can see this v square term is there. So actually it is energy. Now this equation is related to pipe flow. Let's say if I have one pipe like this, okay, and this is condition 1, this is condition 2, and fluid is flowing like this. So P1 is here, V1 is here, M1 is here. Let's say we are assuming liquid flow, single phase liquid flow, and P2, V2, M2, and assume some elevation also there. Okay, Z is not not 0. It may have, let's say, 1 meter, for example. Okay, how Z will be like this? Z will be like this. Pipe is there, and this is the Z. This is height from horizontal. Now, how to apply the Bernoulli's equation there? Bernoulli's equation will be applied like this: P1 by rho 1 G1. This is rho 1. This is rho 2. Okay, plus V1 square by 2G plus Z1 equals P2 by rho G, not G1. This is gravitational constant, so we cannot put G1. It is only G, plus V1 square by 2G plus Z2. Okay, so inlet pressure or inlet energy, exit energy must be equal. So at inlet condition, P1 by rho 1 G, velocity V1 square by 2G plus Z1, elevation of inlet. For example, if pipe is made such a way that from ground distance is 100, another end distance 200, so Z1 is 100, Z2 is 200. So that way we calculate. And how the Bernoulli's equation came up? If you are a mechanical engineering student, you may have done already the experiment, actually venturimeter experiment. So there you have one pipe like this, okay, and you have one manometer, U-tube manometer. Fluid is flowing like this, fluid flow, okay, and this is called U-tube manometer, U-tube mano. It's a very simple instrument. It is having one pipe only, and pipe will have some high density fluid. Let's say mercury may be there, or any high density fluid you can put there. Okay, and when fluid is not flowing, the mercury will be like this. It will be equal height. Okay. Now, if fluid flow starts, let's say Q flow rate you are giving. So what will happen? The larger diameter pipe section, they will have low resistance, low pressure, but smaller section will have higher pressure. Same flow rate you are getting. Okay, but if velocity changing, then your pressure also changing. Okay, if you see Bernoulli's equation, velocity increasing, so pressure will be reducing. If velocity decreasing, pressure increasing. So in that case, what will happen? High velocity, pressure will be lower. So this column will be 2, 1. So section 2 will have lower pressure actually. Velocity will increase because narrow section, same flow rate, larger diameter. Okay, here velocity equals Q by A. You should remember, A means area of the pipe. So here A1, A2. So at point A1 in this U-tube manometer section, the area is A1. So flow rate is Q, velocity will be V1. And at 2, so this is V1, this is V2. So what happens? V1 will be, V2 will be more. So V2 will be more. Okay. So if you put this formula, so you are getting more V2. When you are getting more V2, V1, P2 will be, so P1 will be more than P2. Okay, so P1 is here. So when P1 is more, P1 is higher, my column, okay, the difference you will have. So when you getting certain difference, so you can assume that how much pressure drop is happening in between this pipe. Okay, this is the Bernoulli equation. This so to prove this P1 by rho 1g, this equation, this is one universal equation, and to prove this one you can use manometer based fluid flow, and you can check. Many mechanical engineering laboratories in the colleges, there will be this experiment, because it is the very simplest experiment available to check the pressure drop through pipe, and relation between P1 and P2, V1 and V2 you can calculate. And Bernoulli equation, actually it is not, it is conditional. When you have no friction, we are assuming here, if we are assuming there is no pump or other thing working, and there is no internal energy transfer. Internal energy transfer, for example, one heat transfer happening, you are giving lots of heat at one end. This is a long pipe, one end you are giving lots of heat. So because of heat, your energy will change. This is energy equation. So you are not changing energy, but if you are giving certain energy or taking out energy, or you are giving energy through your pump, or you are giving you are taking away energy, internal energy somehow, then this equation will not hold. Then you have to use modified form of Bernoulli's equation. So what is the modified form? So modified form of Bernoulli's equation. So in modified form, what do you do? P square by 2g plus V square by 2g plus z plus friction factor term, friction or pump or any other energy thing going into the system or going out of the system. So that also you have to include. That will be modified form. Then Bernoulli equation will be valid. But if you are using simplest form, then you have to say this is only simplest form. We are not assuming. We are assuming that there is no energy coming into or going out from the system. But if you are using generalized form, you want to, or modified form, then you have to use all the terms, friction, pump. If you have any other system, that also you have to add. Then that will be modified form. And you have to calculate friction separately. You have Moody's diagram or Darcy-Weisbach diagram. From there you can get how much friction you can get, and pump, how much energy you are putting because of pumping system. For example, you are lifting fluid from one floor to 10th floor, or you are lifting fluid to Burj Khalifa. Okay, so in that case, like 134 floor you are lifting. So in that case, pump must be working. So piping friction loss plus pump energy input. So all these things you have to calculate. From wellbore also, if you have artificial lifting system, then again you have to calculate pump, how much energy it is delivering. So that also you have to include. You have to calculate your net positive suction head and other losses. So many things will come up. But simplest form is that P square by 2g, V square by rho g plus z equals constant. So that one you have to remember all time. That formula is universal, and normally in exam will not give, but modified form maybe sometime will give or sometime will ask, okay, include this one. Okay, Darcy's formula on pressure drop. So Darcy, he developed some formula for pressure drop. The formula is like this: V square by 2g plus P by rho g plus z equals C. Actually, this is Bernoulli's formula, but he tested different way. How he tested pressure drop through pipe? He used one pipe, okay, and he took one reservoir like this, and exit also having some storage, and he put some piezo manometer pressure measurement system. Okay, so when this is 1, this is 2, and at 1 he got very high pressure, at 2 he got very low pressure, and this is filled with actually sand. Okay, because of sand, fluid got lots of resistance. So P1 to P2 pressure got changed. Okay, using that formula he proved this formula, V square by 2G plus P by rho G plus Z equals 0, is equal constant. Okay, now we have seen this Bernoulli's formula through the Darcy's experiment. Now we'll try to implement for our pipe flow. So what is the formula? Del P is the pressure drop. Del P is the pressure drop. P1 minus P2. So how P1 minus P2 like this? It is like this. This is 1. This is 2. This is theta. And this is Q1. This is Q2. This is P1. P2. Mass flow rate. We are assuming liquid flow single phase. So mass flow rate. Mass flow rate must be same actually, and we are assuming liquid flow single phase, so we are assuming density almost constant. So density also we can take, so density will almost constant, so rho 1 minus rho 2 will be 0, mass flow rate will be constant, Q will be constant. What will be changing? Velocity will be changing. Velocity will be changing. And what other terms are there? Okay, diameter D1, D2. Other terms, velocity, they are using U. Okay, I will not write V, I will write U. I will write U1. Okay. Now G by GC, G equals acceleration due to gravity in APS unit. So 32 30 pound per second square. GC also, the ratio will be 1 actually. If you are changing location, then GC value will be different. Otherwise, normally we are assuming G by GC equals 1. It's 32.17 something value. So there. For exact value, you just follow the book. Rho is the density. Del Z. Z is here. Z is here. Z or del Z. Rho is density. G by GC. GC value again 32. And del U. U is velocity. Fluid velocity. And here fanning friction factor, F is fanning friction factor. So normally fanning friction factor will be obtained from Moody's diagram. So Moody's diagram I will explain later. When you are using Moody's diagram and you are getting certain friction factor value, for fanning friction factor you have to Fm divided by 4. So Fm is Moody's friction factor. Fm is Moody's, MODY is Moody's friction factor, CTION factor, and D is the diameter. And every time you have to take proper unit. If you are not taking proper unit, then everything will be wrong. So here P1 and P2 you are taking PSI. So both are PSI. G by GC unitless, it is becoming. Rho is the density. So pound mass divided by kg per meter. So FTQ. Del Z again it is fit. D also again fit. L is the length of the pipe. Length of the pipe L. Length of the pipe is L. Okay. Now, if you want to calculate the pressure drop through the pipe, first you have to know these values friction factor. How to get friction factor? First you have to calculate Reynolds number. Why Reynolds number is required? Because the friction factor is dependent on Reynolds number. So how to calculate Reynolds number? Reynolds number for pipe flow NRE equals du by mu. Du rho. Okay, du rho by mu. Now, how to calculate U? How to calculate U? U is fluid velocity. So, Q by A. So, if I give Q flow rate, then you can divide by area. So, this is area A1, this is area A2. Okay. So, your velocity will be different at 1 and 2 locations. and pipe diameter rho will be given, mu will be given. Now if you have laminar flow, then friction factor value you can calculate from simple manual calculation, 16 by n r e. But if you have turbulent flow, for turbulent flow normally we use this equation 1 by ff, this equation, big equation for turbulent flow. Turbulent flow, and this is for laminar flow. And this is called field unit. Okay, so if you are using field unit, then you have to use this 1.48. Because of this unit change, you have to use this one. And if you are using SI unit, normally it will be very easy. But once we give data in field unit, again converting to field unit to SI unit, sometimes it will be difficult. You have to remember lots of digits. So if you can remember field unit conversion also, that will be very good. Now using the previous formula, let's try to solve one problem. Given data, oil production rate 1000 barrel per day, gravity 40 degree API, viscosity 1.2 cp, tubing size 2 and 7/8 inch, tubing is 15 degrees slanted from the vertical, tubing wall relative roughness 0.001, pressure drop over 1000 feet of tubing. You have to calculate. So oil production rate is given, and first you have to draw the tubing. Okay, this is tubing, and okay, I'll draw something different. This is tubing, and this is given 15 degree. Okay, and this is 0.1, this is 0.2, and tubing length. Okay, so tubing length is given 1000 feet. 1000 feet. So at 1, assume velocity v1, u1, and u2, area a1, a2, mass m1, mass m2. Now first you have to calculate fluid velocity. So how to calculate fluid velocity? So q is given 10,000 1000 barrel per day, BPD, barrel per day. Now q is 1000 barrel per day, u equals 4q divided by pi d square. So pi by 4 d square 4q. So it will be like this, 4 into this unit conversion 5.615 into 1000 divided by pi value you put, then you convert the diameter 0.188 square, and you convert into second. That barrel per day you have to convert in seconds, so 186,400. So finally this gives 2.34 feet per second. Because it is there is nothing information given whether piping diameter is changing from 0.1 to 0.2. We are assuming the same piping diameter, so U will be same from inlet to outlet because density is constant. It's oil, so we are assuming density change also negligible. Now we have to calculate oil specific gravity. So oil specific gravity will be 1.41 1.5 divided by API plus 131.5. So it will give a result like this, 141.5 divided by 40 divided by 40 plus 131.5. So finally it is coming 0.825. So oil density, this is oil specific gravity. Oil density rho oil equals 62.4 gamma O. So finally it is coming 51.57 lb pound mass cubic feet. And elevation, because of elevation the value of Z or difference of Z, del Z equals cos 15 degree L. L means tubing length. Okay, so that will come 966 feet. And okay, U is there, D is there, and Reynolds number 1.48 Q rho divided by D mu. So this will come 281, which is more than 22,000. So this is a turbulent flow. So we are getting turbulent zone. So when you are getting turbulent zone, so here one thing I forgot to mention is D, tubing diameter. When people it problem will be given as a tubing size, so actually it will be outer diameter will be given. So inner diameter you have to assume, or one table will be given, or will give the inner diameter. If you are not using the inner diameter, using outer diameter only, your problem will be wrong, your solution will be wrong. So 2 and 7/8 inch tubing, inner diameter will be 2.259 inch. Okay, so this one will be coming from API tubing design table, and normally the data will be given. If not given, then you assume some thickness of tubing and you calculate, but do not take it is as it is, because this is outer diameter and fluid will be flowing through the inside of the tubing. So inner diameter you have to calculate. Okay, you can assume some inner diameter, or you can get data from table given to you. If you are using exactly as it is for your flow calculation through tubing, then it will be completely wrong. So that gives D value equals 2.259 divided by 12 equals 0.188 feet. So now, because you got RE value 28115, so you can use chains correlation. In previous slide we have seen the chains correlation, this big correlation, this one. You can use this correlation to calculate FF, friction factor, fanning friction factor, or you can use the chart here. You can use this chart. This is called Moody's diagram. So you will get FM value, not FF value. So if you want to calculate, the FM divided 4 you have to do. So in previous section we have seen our Reynolds number 2 into 28115. Okay, so in that case it will be somewhere else. Okay, and then you have to calculate the piping roughness or relative roughness value. What is the relative roughness? When you see the pipe very much rough or small roughness is there, so that exact value of roughness divided by piping diameter, that will give relative roughness. So sometimes we give the relative roughness value to in the problem. Okay, so in that case pipe roughness value is given as 0.001. So 0.001 is given. So for example, Reynolds number value is coming like this, then we'll go like this and we'll reach like this. 0.001, maybe it will be this range, it will be somewhere else. Okay, and 0.001 will be like this, and we can get this friction factor value. So friction factor value, this is manually drawn, that's why the value will be a little bit different, but when in exam maybe we will give exact Moody's diagram, so you can get exact value, but it will be this picture actually closely resembles the exact Moody's diagram. So first you have to get Reynolds number value, then you have to check Reynolds relative roughness value. But if relative roughness value is 0.02, roughness value can be like this also, 0.003, 0.004, 0.0001, maybe 0001. So if you go down, your roughness is going down, your friction factor also going down. If you are increasing roughness, pipe is more rough, then in this case your friction value also increasing. Okay, if you see the left side friction value, it is gradually increasing from bottom to top, right? So relative roughness increasing means the roughness on the surface is increasing. Same pipe, roughness increasing means your friction also increasing. Okay, and if you have laminar flow, you have seen the formula, F equals Re 16 by Re. Okay, so if your Reynolds number value is very low, so in that case you can use directly formula 16 by Re, or you can use this table, this chart also. Like this chart is having one straight line, this is called laminar flow region. But if your Reynolds number increasing, then you have to reach to turbulent region, turbulent flow region. So in that case you have to check Reynolds roughness number, and roughness number will give friction factor. Higher roughness implies higher friction factor or higher pressure drop. So from this table, actual table, we got roughness value, F Moody's friction factor we get 0.0265. But yeah, so F we calculate, or we get Moody's friction fanning friction factor 0.0066. So from there, if we put all the data, then del P or pressure drop will be coming is like this: G by GC rho del Z plus rho 2GC del U square plus this friction factor term 2FF rho U square L GC by GC into D. So this U value is 0 because there is no piping diameter change, and flow rate same, mass flow rate is same, so U also same. So only these terms are there. So G by GC is 1. So this rho value is given 51.57. It is calculated into 966 plus 2 into 0.0066 5157 2.34 square into 1000 piping length, GC 32.17 actually exact value, into 0.188. So finally it is coming 350 psi. So students are suggested to practice similar sort of problem. Some problem are given in the book, textbook also, Gu and Galambar book for petroleum production engineering. You should try to practice. Okay, next day we'll try to cover the multi-phase flow. Thank you very much.